In the last class, we discussed about the configuration of feed forward control scheme, and today we will discuss the design of feed forward control schemes. So, first we will discuss the generalized form of feed forward controller. Generalized form of feed forward controller. Fine. So, for this we first draw the process. So, there are two transfer functions, one is GP, another one is ZD. D is the disturbance and M is the input to the process. Output is Y. Fine. So, this is the block diagram of the open loop process. This is the block diagram of the open loop process. Now, we can represent this process mathematically as output y bar s, which is equal to GP m bar s plus ZD d bar s. This is the representation of the open loop process shown here. Fine. Now, our target is to keep the y at its set point value. Our target is to keep y at its set point value. This is our target. Fine. So, accordingly the feedback controller feed forward controller is required to take the control action. Feed forward controller needs to take action to keep y at its desired value, that is y set point. So, if we substitute y equal to y set point in this equation, then we obtain y set point is equal to GP s m bar s plus ZD s d bar s. This expression we obtain just substituting y equal to y set point in this open loop expression. Now, if we rearrange this equation, we obtain m bar s, which is equal to 1 by ZDS y set point bar s minus d bar s multiplied by ZDS divided by GPS. If we rearrange this equation, we get this expression in the form of m, which is the input to the process. Now, we can write this expression as m bar s equal to Z set point s y set point bar s minus d bar s multiplied by GCS. GC is the transfer function of the controller and GSP is the transfer function of the set point element. G suffix SP is the transfer function of the set point element and GC is the transfer function of the controller. Now, if we compare the last two equations, we obtain GSP equal to 1 by GDS. If we compare the last two equations, we obtain GSP equal to 1 divided by GDS. This is transfer function of the set point element. Similarly, we obtain GCS as GDS divided by GPS. If we compare the last two equations, we obtain similarly the expression for controller. This is the transfer function of the feed forward controller. Feed forward controller. Fine. So, these two transfer functions we obtain. In the next we will develop the block diagram of this feed forward control scheme. We will develop the block diagram for the feed forward control scheme. First we will draw the open loop process. The open loop process includes two transfer functions, one is GP, another one is GD. So, this is the open loop transfer function. Fine. Next we wish to include the feed forward control scheme with this open loop transfer function. You see the expression. This is the expression of the feed forward control scheme. This is a comparator. This is D. See here minus D is involved. So, we can put here minus sign. Next GSP YSP. So, we can put here set point element and input to this set point element is y set point. This is positive. Fine. The output of this comparator is suppose error and this is the error z set point y set point minus d, that is the error. This error is, this is suppose the error epsilon. This error is multiplied with GC. So, we can put here one block for GC. Fine. Output is M. This is the output. So, first this disturbance is measured and this disturbance is subtracted from GSP multiplied by YSP. So, we can consider GSP multiplied by YSP minus D as error signal. So, this is basically the error. Then this error is multiplied with GC, therefore, GC is placed here and this output signal of this controller is M. So, this is the block diagram of the feed forward control scheme. Fine. Now, in this block diagram you see the final control element and measuring device are not included. The final control element and measuring device are not included. If we wish to include that, then we obtain the closed loop block diagram. Somewhat like this. This is disturbance. So, first we measure this disturbance using one measuring device which has the transfer function of GM. Then this measured disturbance is compared in a comparator. This is the set point element, then here controller, here final control element. Fine. So, this is the block diagram for the feed forward loop. Block diagram for the feed forward loop. Fine. We have just included here one measuring device and final control element. Now, we will note down few important points on this feed forward control scheme. See, if we see the equation of the feed forward control scheme, this one, it is obvious that the feed forward controller is not like P or PI or PID controller. If you compare this equation with any expression of P or PI or PID, it is obvious that the feed forward controller is not like P, PI or PID controllers. This is the first important point. From the equation of feed forward controller, it is obvious that it is not like P or PI or PID controllers. It is a special purpose computing machine. It can be viewed as a special purpose computing machine. It can be viewed as a special purpose computing machine. Second important point is, if you see this equation, it is obvious that the feed forward controller heavily depends on the process model. You see, in this equation GD, GP transfer functions are involved. That means the feed forward controller depends heavily on the process model. It depends on the process model. Fine. It is impossible to develop the accurate model in practice. Practically, it is not possible to develop the accurate model. So, we cannot achieve perfect performance from this feed forward controller. Practically, it is not possible to develop the accurate model, and we can consider this is a drawback of feed forward controller. Fine. Next, we will take one example to discuss to derive the design equation for this feed forward controller. We will consider an example of this feed forward control scheme. So, we will take a heating tank system which we discussed earlier. Fi is the input flow rate, Ti is the temperature, F is the outlet flow rate and T is the temperature. Liquid height in the tank is H and T is the temperature. Now, the heating medium is passed through this heating coil. Suppose steam is the heating medium and it has the flow rate of Q, I mean it carries Q amount of heat. Fine. Here F, Fi both are volumetric flow rate, volumetric flow rates. H is the height of liquid in the tank. A is the cross sectional area of the tank. A is the cross sectional area of the tank. H is the liquid height in the tank. Fine. Now, for this process we developed earlier two equations. One is based on mass balance, another one is based on energy balance. So, we obtain the mass balance equation as A dH dt equal to Fi minus F. This is the mass balance equation. Similarly, if we obtain the energy balance equation as AH dt dt equal to Fi Ti minus T plus Q divided by rho Cp. This is the energy balance equation, this is the mass balance equation. To discuss the feed forward control scheme, we assume that Fi and F both are equal and they are constants. Here we are assuming that Fi equal to F and that is constant quantity. Accordingly, From the mass balance we obtain dH dt equal to 0. That means H is again a constant quantity. So, what is our control objective? Our control objective is to maintain the temperature. So, temperature is our controlled variable. What is the corresponding manipulated variable? Q. We have assumed that Fi is a constant quantity, therefore, Ti is the load variable. Therefore, Ti is a load variable. So, next we will derive the design equation for the feed forward control scheme. Next we will derive the design equation for the feed forward control scheme. So, we will start from the energy balance equation, which is AH d capital T d small t equal to Fi Ti minus T plus Q divided by rho Cp. This is the energy balance equation which we have written earlier. Now, we can write this equation as V divided by Fi. We are just dividing both sides by Fi. We are just dividing both sides by Fi. Then we obtain V divided by Fi dt dt plus T equal to Ti plus Q divided by Fi rho Cp. Here we assume V equal to AH. Fine. So, by dividing both sides by Fi and rearranging, we obtain this equation. In the next step, we can write this equation in terms of deviation variables as V divided by Fi d T prime dt plus T prime equal to T I prime plus Q prime divided by Fi rho Cp. This equation is written in terms of deviation variables. Fine. Here 3 deviation variables are involved. One is T, Ti and third one is Q. Now, if we take the Laplace transform, we obtain T bar prime S equal to T I bar prime S divided by tau S plus 1 plus 1 divided by Fi rho Cp 1 divided by tau S plus 1 Q bar prime S, where tau is equal to V divided by Fi. This is the retention time of liquid in the tank. Retention time of liquid in the tank. If we take the Laplace transform of this equation and after rearranging we obtain this expression, where tau is a retention time of liquid in the tank. As mentioned earlier, the objective is to keep the temperature T at its set point value. This is the objective. Accordingly, the feed forward controller computes the control action. The objective is to maintain the temperature T at its desired value, that is T set point, and accordingly the feed forward controller takes action. So, substituting TSP in place of T in this equation and rearranging, finally we obtain Q bar prime S equal to Fi rho Cp tau S plus 1 T set point bar prime S multiplied by T I bar prime S. Fine. Substituting T equal to TSP in this expression and rearranging, finally we obtain this expression, the expression of Q. Fine. So, this is the design equation of the feed forward control scheme. This is the design equation of the feed forward control scheme. Now, can we configure the feed forward control scheme considering this equation for the heating tank system? In the next, we will try to configure the feed forward control scheme incorporating this expression, I mean applying this expression. So, this is the example system. Fine. In the feed forward control scheme, the disturbance is measured. Here disturbance is T I. So, we can measure this T I using one temperature measuring device. Fine. Then this T I is compared with the set point value. Fine. You see TSP tau S plus 1, this one, minus T I, this is T I. Then the output of this error signal is multiplied with Fi rho Cp. So, this is Fi rho Cp, and that is basically Q prime. Agree? Tau S plus 1 multiplied by TSP, that is this one, minus Ti, minus Ti. So, this part we can consider as error. So, this is error. Then this error is multiplied with Fi rho Cp, this is Fi rho Cp, and output is Q, and that is written here in terms of deviation variables. Agree? So, this is a feed forward control scheme for the heating tank system. This is the feed forward control scheme for the tank heater. Fine. Now, if see this feed forward control scheme we have developed considering the dynamic equation, dynamic energy balance equation. Therefore, this feed forward controller is sometimes called as dynamic state feed forward controller. Since we have used the dynamic energy balance equation for deriving the feed forward controller, therefore, this is sometimes called as dynamic state feed forward controller. Fine. Similarly, we can derive the steady state feed forward controller. Similarly, we can derive the steady state feed forward controller, and for steady state feed forward controller we write the energy balance as this. We have just considered dt equal to 0. Left hand side of the energy balance equation we considered 0. Then we obtain this steady state equation. Fine. Now, if we rearrange it, we obtain Q equal to Fi rho Cp multiplied by T minus Ti. If we rearrange this steady state form of energy balance equation, we obtain this. Fine. Now, this is the design equation. Sorry, we just have to put T equal to T set point, then finally we obtain this, and this is the design equation for the steady state feed forward controller. This is the design equation for the steady state feed forward controller. Now, if you compare the dynamic state feed forward controller and steady state feed forward controller, we see that only this term does not exist for steady state feed forward controller. For steady state feed forward controller, this tau s is equal to 0. Fine. We can get the steady state feed forward controller just substituting tau s equal to 0 in the dynamic state feed forward controller. So, we have configured the dynamic state feed forward controller with this heating tank system shown here. For steady state feed forward controller, you just write inside this block 1. For steady state feed forward controller, you replace tau s plus 1 by 1. Fine. So, that is the steady state feed forward controller. In the next, we will discuss another advanced control scheme, that is ratio control. We will discuss another advanced control scheme, that is the ratio control scheme. This ratio control scheme is a special type of feed forward controller. Ratio controller is a special type of feed forward controller. Its objective is to maintain the ratio of two variables, therefore, the name. Its objective is to maintain the ratio of two process variables. The ratio of two process variables at a specified value. Its objective is to maintain the ratio of two process variables at its specified value, and these two process variables are usually flow rates. So, the objective of the ratio control scheme is to maintain the ratio of two flow rates. Fine. Both flow rates are measured, but only one is controlled. Both flow rates are measured, but only one can be controlled. Only one can be controlled. Fine. Now, which is controlled, that is called manipulated variable. So, this is manipulated variable, and another flow rate is not controlled, that is basically disturbance variable. The variable which is not controlled, that is basically disturbance variable. So, the objective of the ratio controller is to maintain the ratio of two flow rates. Both the flow rates are measured, but only the manipulated input is controlled. The flow rate which is not under controlled is the disturbance variable, and since this is not controlled, it is called as wild stream. Fine. Since the manipulated variable is not under control, it is called as wild stream, and the ratio denoted by R is equal to U divided by D. U is the flow rate of the manipulated input, flow rate of a manipulated variable, and D is the flow rate of disturbance variable. Fine. Since the flow rate of manipulated variable and flow rate of disturbance variable, they both are measured. So, sometimes they are written as U measured divided by D measured, and accordingly the ratio is denoted by R suffix M. Since the manipulated input and the disturbance variable both are measured quantity, therefore, they are sometimes denoted by U suffix M and D suffix M. Accordingly, the ratio R is denoted by R suffix M. And another important thing is that both u and d are physical variables, not deviation variables. U and d both are physical variables, not deviation variables. Fine. In the next, we will try to develop the ratio control configuration. In the next, we will discuss the ratio control configurations. So, this is one stream. Say this is the disturbance stream. Fine. And this is another stream. Which we can call as manipulated stream U, and this is D. Now, it is mentioned that both the flow rates are measured. So, we can employ one flow measuring device, that is suppose FT1 for measuring the flow rate of disturbance stream. Similarly, we can measure this manipulated variable using another flow measuring device, that is a FT2. So, this is say D suffix m, and this is suppose U suffix m. It is mentioned that both the flow rates are measured. Accordingly, we can employ one flow measuring device for disturbance stream, another flow measuring device for manipulated input. Now, in the next, it is required to compute the ratio. So, this is representing the divider. This is the divider which is computing the ratio um by dm. In this divider, Rm is calculated using this expression by dm. So, the output of this divider is basically R suffix m, measured ratio. Fine. This measured ratio is compared with the set point value of reflux ratio R. RSP is the set point value of ratio. So, the output of this comparator is basically the error signal. Output of the comparator is error represented by epsilon, and this output goes to the ratio controller. ZRC is the transfer function of the ratio controller. Then the output of this ratio controller is implemented through the control valve. Fine. It is mentioned that both the flow rates are measured. Accordingly, FT1 can be employed to measure disturbance variable, FT2 can be employed to measure this manipulated variable. Then this is the divider element in which the the ratio Rm is computed considering this expression by dm. So, output of this divider is Rm, which is compared by the set point value of this ratio RSP. Then this error signal goes to the controller. GRC is the transfer function of the ratio controller, and the controller action is used to control this manipulated input. So, this is the ratio controller. This is the ratio controllers. Fine. So, I am repeating again the steps. Both the flow rates D and U are measured. Then compute the measured ratio. Compute the measured ratio Rm, which is equal to divided by dm. Fine. Now, the output of the divider element is sent to the ratio controller. Output of the divider element is sent to a ratio controller. Fine. In this ratio controller, first the error is calculated. First, the error is calculated by comparing Rm with RSP. Fine. And then the ratio controller takes action. Now, this ratio controller is typically a PI controller. Ratio controller is typically a PI controller. Fine. Now, at the beginning I have mentioned that the ratio controller is a special type of feed forward controller. Now, we are saying that the ratio controller is a PI controller, which is feedback controller. So, what is the justification behind this? Actually, in this ratio control scheme, the disturbance is measured. Therefore, the ratio control is in essence is a special type of feed forward controller. Fine. In this ratio control scheme, the disturbance is measured. Therefore, the ratio control is in essence is a special type of feed forward controller. Next, we will discuss the applications of this ratio controller. Can you give few examples where we can employ this ratio controller, where basically the ratio is involved? Like one example is reflux ratio in distillation. So, to control the reflux ratio in distillation columns, the ratio controller is used. To maintain the reflux ratio in distillation columns, the ratio controller is used. To control the ratio of two blended steams, maintain the ratio in a blending process, the ratio controller can be employed. To maintain the stoichiometric ratio of reactants in the reactor or reactive distillation, maintain the ratio of stoichiometric to maintain the stoichiometric ratio of reactants to a reactor or reactive distillation, the ratio controller can be used. If any reactant is in excess, that can come out as the product in the product, and that degrades the product quality. Therefore, it is required to maintain the ratio stoichiometric ratio of reactants which are fed to the reactor or reactive distillation. To maintain the fuel air ratio to a furnace, the ratio controller can be employed. To maintain the fuel air ratio to a furnace, the ratio controller can be employed. So, these are the applications of ratio controller, and ratio controller is extensively used in chemical engineering processes. So, today we discussed the derivation of design equation for the feed forward control scheme. We discussed the feed forward controller with taking one example, that is tank heater, and finally we discussed a special type of feed forward controller, that is ratio controller. Thank you.